Okay, so let's continue our discussion on using transformers in large data sets to obtain pre-trained models. And here we want to switch from the vision transformers to language models. So the vision transformer idea actually came after what we are going to talk about today. Transformers were initially developed to handle text data, initially in machine translation, which had an encoder and a decoder part to take in a sequence and output another sequence. But then later different parts of the transformer proved to be useful. And BERT here is a way of encoding text, just like what we did for vision transformers to classify that text. But we first saw that idea in image classification. And the main reason was we are very familiar with that since we developed the CNNs there. And we already saw this potential for learning representations across images and text. So that basically helped us to double down on this idea of transfer learning, learning a pre-trained model and then use it for specific tasks. We want to try that idea in text. And we look at three different architectures, all transformer based. BERT, which is the encoder part of the transformer. GPT is only the decoder part. And T5 is the entire architecture. So these names, BERT, GPT, and T5, are like the most famous person in this family, basically, that becomes like a last name, really. But for example, in the decoder part, we have llama models. That is still an autoregressive type of model. Okay, so we discuss how to train these models, and later we want to fine-tune them, right? And we discuss the way that we are training them that we call self-supervision that is somehow different than what we did for vision. So back to computer vision. Let's say we want to classify flower types and we have, let's say, 5,000 labeled flower images. And we want to train a CNN with 50 million with 50 million parameters. And we need a GPU and maybe a few days of compute or less, depending on the resources that we have. The question is, should we train from scratch? The answer back in 2012 was no, because we will going to be overfit badly with this number of parameters and this number of images. We cannot get a good model. But now that we have a trained CNN, possibly on a very large data set, for example, ImageNet, we can use it and fine-tune for our specific problem. We have done this before. And the idea is there are some universal features that the pre-trained model on the large data set learn, and we don't need to learn that anymore, and we can transfer them to the new task. Hence, we can copy the pre-trained CNN and freeze most of the layers and only train a few layers that corresponds mostly with the new head that is using the same features and predict different classes. So after 2012, once we had these pre-trained models, we can fine-tune them on smaller task-specific data sets that sometimes is very difficult to collect, for example, medical imaging, due to many reasons, for example, privacy-related standards and compliances, or getting good labeled data. But now that we have this setup, we can fine-tune our neural network for these finite data sets. Hence, this allows us to have specialized networks on different specialized domains. So by 2015, basically, this idea was a standard practice in computer vision. Now the question is, can we do the same for text? If images have edges, textures, and shapes, well, text has grammar, syntax, and semantics too, that are general features and we can learn. Well, to answer that, first we have to say, well, for the computer vision, we had this very nice data sets that are labeled and have this clear task for classification. Do we have the same for text? Well, not really, because a comparable labeled data set for text is either non-existing due to the humongous effort that is required for labeling them, or sometimes really the task is not set in stone, and the task is oftentimes very fluid in text. So that's a problem, and how can we solve that? Well, the answer is maybe we don't need that. And that's how we get to self-supervised learning. So the idea is, well, text contains its own supervision. Yes, we may not have like cleanly labeled sentences, but we have unlimited unlabeled text. For example, we have Wikipedia dataset with billions of tokens, different book data sets, again, with billions of tokens. We have web pages that we can design crawlers and scrapers to collect data from. And within text, we have an inherent structure. For example, we can hide a word and the model can predict that. We can basically hide half of the sentence and the model can generate the other half. Basically, what I'm trying to say is text itself provides labels if we look differently. This is known as self-supervised learning, which the model creates supervised tasks for itself from this unlabeled data. So some of the question, for example, let's say we have a sentence like, I love this red car, and then we can mask a word here, red, for example, and make up a task to predict that token. So the model can do the entire steps. No human label is needed. Another way of making up labels is to do next token prediction. So we have this sentence and then we hide the last word or last token and we ask to predict that. This is known an autoregressive task. You can think of other made up super signal for shuffling sentences and asking to restore them, where again, we have the original document that tells us the order. So great, you can do this for text, but why we didn't do it for images at the first place? Well, the main reason was for text, we have a finite vocabulary, and it's easy to design these self-supervised tasks. And often it even seems natural to do it. For example, predict this word. I mean, we do games like that. Given some context or answers for some question, we ask the other player to predict the word. And then we can use this very efficient cross entropy loss, for example, here. That's not the case for images, and the main reason is there we're dealing with continuous data, and there's not really a finite vocabulary. We're talking about pixel values, and it's very hard because of that much larger degree of freedom to do the training. There are some modern way of doing self-supervised learning for vision now that I'm going to skip, but back then that was not the main way of training computer vision models. Again, these new updates are available now because of the advances in the NLP field that trickled down to computer vision. Okay, so the transfer learning will look different now. And here we have this pre-training stage for text that is trained on this massive unlabeled corpus of text. We're talking about billions of tokens. And this is done in a self-supervised manner. And this way, the model learns the general features of the language. And then we can transfer that to more specialized tasks. For example, with thousands of examples that has a specific task that we care about. Later, we will see that even given if we have a rich pre-training without any further training and just by giving some context within a prompt, we can get the answers for our question. And that's where things become very interesting. Okay, so let's not jump ahead and continue from the BERT family that started this paradigm of self-supervised learning. So here we focus on BERT, which is the transformer-based version of them, which is basically an encoder transformer trained in a self-supervised manner and language models, and then fine-tune on different tasks. The original paper for BERT showed that for all of these different NLP tasks, BERT achieved state-of-the-art performance. This fine-tuning on these tasks often needed only a few thousands of examples. So this really changed the landscape of NLP, because before BERT, if we wanted to train a model for a specific task, we needed to design its own architecture and its own large label dataset, and eventually achieve a model that only does a specific task. But after this paradigm shift, one pre-trained model can be fine-tuned for different tasks, often with small data sets, and achieve strong performance. And that's how transfer learning became default in NLP. So we discussed transformer architecture, and we said it's modular. It has this encoder, decoder modules. And for these three different families, for example, BERT only uses the encoder, GPT only uses the decoder, and this sequence-to-sequence models with this flagship T5 model uses both. So if we want to use both, we need a cross-attention, right? Otherwise, self-attention within the encoder or decoder is enough. So whenever we have only the encoder, we don't really need the causal masking. So we can look both ways. And that's how the bidirectional way of training can be included in BERT, for example. And for some T5 or sequence-to-sequence models also, as long as we're not decoding one token at a time, we can also train them in a bidirectional ways. Okay, so let's zoom in into BERT, which only uses the encoder transformer. Like I said, it's a bidirectional self-attention, meaning that every token can attend to all other tokens, and there's no causal mask. We really don't need that. And the output can be a contextual representation, something like the CLS token that we discuss in Vision Transformer. Just like Vision Transformer, they can be great for classification, for example, sentiment analysis. They can fill or replace tokens, and they can also understand tasks in case we want to use that for another reason than classification. Okay, so let's look at how we are doing this self-supervised learning in BERT. So the procedure for that was to select 15% of token randomly and replace 80% of that 15% with mask tokens, 10% of that 15% with random token. Basically, we replace them with randomly chosen token from the vocabulary, and then choose another 10% and keep it unchanged. So let's zoom into why this 15% is spent like this. Note that we choose these tokens and we ask the model to predict them. When we replace the token with mask token, basically the mask token is not providing any information about the original token. So the model has to look around and seek context for that. The 10% of tokens that are replaced with the random token is a way to reduce the train test mismatch. What I mean is basically during the pre-training, if the model only sees the mask token, it may only worry about the token's representation when it's a mask. So it gets lazy with the representation of the non-mask tokens. But by swapping in a random word chosen from the vocabulary, we force the model to learn that any word can be potentially wrong. So it has to rely on the context to verify or correct the token that it's looking at. So now the question is why we keep 10% unchanged. The reason is this is a way of balancing out this 10% wrong tokens. Because otherwise, if we don't have this and we have only this, basically the model learns this bias that any non-mask token that I'm asked to predict is probably wrong. But with keeping this unchanged tokens, we force the model to use the context to confirm if the word is correct. So, in summary, the mask tokens forces the model to use the context. The random tokens reduces this train test mismatch. And in conjunction with this unchanged tokens, the model is not sure if a token is correct or random, so it must always be cross-checking it against the context. So that's how we trained the BERT model. Note that this is an encoder model, which means that we don't need to have a causal mask, so we can look from both directions, which makes the model more sample efficient compared to those that enforces the causal masking, like the autoregressive models like GPT. Okay, so how to do fine-tuning? Well, if we have a classification task, just like what we did for vision transformer, we use the CLS token and send it to a softmax to get the logits, and send it to a softmax to get the probabilities. So the token classification task is also called named entity recognition, or NER. So the next task is really sentence pairing. So note there is an additional token here that basically separate the sentences, and it's like a boundary for each sentence. And you already know CLS token. So this helps us to now define tasks on the sentences and somehow do natural language inference, which is basically a way of recognizing this textual entailment that involves logical relationship between pairs of sentences. For example, contradiction, withdrawal, and entailment. So the other family is T5. So T5 architectures are using both encoder and decoder, very similar to sequence models. But here, T5 frames every NLP task as a text-to-text problem. So the original transformer from the paper Attention is All You Need. It introduced an architecture. It didn't really specify any pre-training task, just like BERT, for example. And it was designed for a single purpose, a sequence-to-sequence task, and primarily for machine translation. T5 uses the same encoder-decoder architecture, so no modification in the architecture, but reframes the input and output. And it's trained differently from the transformer. So for example, transformer really, they didn't have a pre-training objective. They were trained in a supervised manner. For example, the machine translation, where we had pairs of sentences, for example, from English to German. Here in T5, we have pre-training, and the difference here with, for example, BERT is here we are not masking tokens, we mask spans of tokens, which makes a more difficult problem. So a span is a subsequence of tokens, and here instead of the mask token, we are using the sentinel tokens, which can be a subsequence, each one of them. And the T5 model is learned to generate them. For example, look at this. We have this sentence that can have different way of span corruption during the self-supervised stage. So the idea here is basically encoder learns to compress and decoder learns to generate. Now let's look at the decoder-only architectures like GPT, where they only use the decoder part or the decoder module, and they use this causal self-attention mask. Because a token at T only sees the previous tokens. Like I said, they are designed for this autoregressive generation tasks. The training is kind of simple because we only predict the next token given all the previous history. And this training is basically exactly the same as the inference, so there's not really a mismatch. And the nice thing about this type of training is we use everything. We are not masking or corrupting a span and then ask the model to predict them. Instead, we ask the model to predict every token. So every token was a labeled question at some point in their life. This makes this decoder-only families very scalable in terms of data efficiency and learning. For example, we have different GPT models from 2018 to 2020, and in particular, the GPT-3 model came up with this idea of in-context learning. So you don't really need to do any fine-tuning as long as you have a good prompt, the model can fill the answer for you. So this is by itself extremely interesting, meaning that we really don't need to do any fine-tuning. We just train the model once and then use it. In other words, no parameter updates is necessary. Instead, we give a prompt, for example, a prompt like this, that basically gives a few examples of what I want to do, which here is translation from English to French, and then ask the model to continue. So given this context, the model basically learns a new task without changing any parameters. And that's where everything is basically can be squeezed into the prompt, and the model already knows to extract the patterns within that context and match those patterns and continue like that. So now, really, if you provide examples in the prompt, each example is like a shot of learning. Like one shot is one example. For example, here in this case, we give two shots and then ask for our question. So this really gives us a very efficient training for autoregressive models or GPT models because it uses the entire data and it's great for generation. We discussed this masking way of self-supervised learning. In BERT, for example, we only use 15% of the data as supervision signal, of course, in a bidirectional way. And this is great for understanding, not really generating. And then we discussed T5, which is using both encoder and decoder very efficiently and get benefit from the both world. Now, there are ways to improve really the BERT models. For example, there is this Electra solution that instead of doing this mask language modeling, it does replacing this 15% token with plausible alternatives and then discriminate if they are real or fake. So this way we basically provide more supervision signal from the same data. But eventually the decoder-only models are, at least for now, they are winning. And mainly because of their simple architecture, they are scaling extremely well. And the in-context learning that emerges out of it gave rise to this chat application like ChatGPT. And they can do basically everything. They can understand tasks, they can generate tasks, and they can also live without fine-tuning. And that's why all of these leading models, GPT-3, GPT-4, Llama, etc., are all decoder only.